diving deep into Matryoshka representation learning (MRL), a fascinating new approach to self-supervised learning in computer vision. Let's unpack the core ideas and delve into the technical details to understand how this method works. The big picture: learning representations within representations. Imagine a set of Russian nesting dolls, each nestled inside a larger one. MRL draws inspiration from this concept, proposing a method where models learn representations within representations, progressively extracting more complex and abstract features from the data. The core idea: self-distillation with nested student-teacher models. MRL leverages a technique called self-distillation with a unique twist. Traditionally, in knowledge distillation, a larger, pre-trained teacher model guides a smaller student model. However, MRL takes this a step further by employing multiple student-teacher pairs nested within each other, building the Matryoshka, multiple nested models. The architecture consists of several encoder networks, each acting as both a student and a teacher. The smallest, innermost encoder learns basic features from the raw input data. Each subsequent encoder, moving outwards, learns from the representations generated by its inner teacher encoder. This creates a hierarchy of representations, with each level capturing increasingly complex and abstract information. The learning process: distillation and contrastive loss. Two key components drive the learning process: distillation loss and contrastive loss. Distillation loss: each student encoder aims to match the output distribution of its corresponding teacher encoder. This encourages the student to learn the representations discovered by the teacher, effectively transferring knowledge across the nested layers. Contrastive loss: this loss ensures that representations from different augmented versions of the same image are similar, while representations from different images are pushed apart. This helps the model learn robust and discriminative features. Benefits of MRL: feature hierarchy and performance gains. This nested learning approach offers several advantages. Hierarchical feature learning: MRL allows the model to learn a hierarchy of features, from low-level details to high-level semantic concepts. This can be particularly beneficial for tasks requiring a deep understanding of visual information. Improved performance: MRL achieves state-of-the-art performance on several image classification benchmarks, outperforming other self-supervised learning methods. Flexibility: MRL is adaptable to various tasks and datasets. The core concept of nested student-teacher models can be applied to different architectures and learning objectives. Implementing MRL: key considerations for deep learning engineers. For those interested in implementing MRL, here are some key aspects to consider. Model architecture: choosing appropriate encoder architectures for each level is crucial. The complexity of the encoders should increase as you move outwards in the nested structure. Loss function balancing: carefully balancing the distillation and contrastive losses is essential for optimal performance. This balance may need to be adjusted based on the specific dataset and task. Training strategies: experimenting with different training strategies, such as curriculum learning, gradually increasing the difficulty of the learning task, could further enhance the model's performance. MRL: a promising direction for self-supervised learning. Matryoshka representation learning offers a novel and effective approach to self-supervised learning in computer vision. Its hierarchical feature learning and impressive performance make it a promising direction for further research and development. As deep learning engineers continue to explore and refine this technique, we can expect to see even more impressive results and applications in the future.